and keeping up with everything, and we're getting close to the end there, so hopefully everybody's hanging in there. We all have the same challenge of staying on track towards the end of the semester, so I encourage you to just keep it up. Everybody keep up the good work, and let's proceed towards the finish line.
Recording started.
Well, good afternoon, everyone. Welcome back to Microprocessors here. And today we're going to continue on a topic that to me is very interesting because we actually interface with many analog devices when we work with digital systems. And so this is an important capability that you will find used in many, many situations. And so being comfortable and understanding the flexibility of an analog to digital converter is going to be important as you start using these in real world applications. Now, one of the things you're going to find is this is also a very, very capable system, and because of that, it has many configuration options that might seem a little bit intimidating. So once you understand what is actually going on under the hood, so to speak, then it's not nearly as intimidating as it might be at first glance. So just kind of reviewing where we are, what we're talking about, we have one 10-bit A to D in our PIC32. Important to know how many bits because that dictates the resolution, and tied to our peripheral bus. So just like many of our other peripherals, we are tied to the peripheral bus, and so as you would expect, we use our peripheral bus clock as well to drive those operations. Something that's important to know as we configure our system. The heart of our system when we are doing estimation of what the input signal is we will use comparators. These are based on the operational amplifier, and what we're doing is we're basically comparing an unknown input voltage to a known reference voltage. And so we want to compare to see whether the input voltage, which we don't know, is greater than or less than a reference voltage, which we do know. And so this is going to be how we basically, in one way or another, determine a value or an estimate for our unknown input voltage. Now, one approach we can use is we could just use a whole array of comparators and do this in just one flash operation. And so these are known as flash A to D converters or direct conversion. So in other words, there's no stepping process. This is all done in just one single step. I compare my unknown reference to a number of known reference voltages, and if I have, in this case I have 7, then I can basically come up with a 3-bit estimate using the combinational circuit, an estimate of my binary input. Now, we talked a little bit about how I could structure my resistors to minimize my error or to reduce my error, but in this point we just want to be aware that I can either use a flash A to D, which tend to be a lot smaller in terms of resolution, or I can use something that's a little bit more precise but takes a little bit more work to be able to come up with the estimate. We talked about using some sort of known references, a whole bunch of different known references to which we're going to compare our unknown, and I use the scale as an example. So in this case, we have the basic operation of our successive approximation analog to digital converter. And this takes a sequence of steps. So first off, I have to have my unknown voltage, and I'm going to include a separate component. We have what is called a sample and hold amplifier. So what I have to do is, because my input voltage will vary during the time I'm doing my conversion process, I need to keep a constant sample steady to which I'm going to compare my known reference. So I will basically, for some interval of time, measure my input voltage. I will basically isolate it and hold that steady value as an input to my successive approximation analog to digital converter. And so the way that the conversion process takes place, so we have an acquisition process and we have a conversion process. So once I'm ready to start the conversion process, I send a start signal to the successive approximation part of the A to D, and now with the clock I'm going to sequence through a number of digital values to generate a known reference voltage or known voltage to which I'm going to compare my unknown voltage. And I will do that and look at the output of my analog of my comparator to determine, is the number I'm presenting larger or smaller. Now the way that so the clock is going to govern how fast we sequence through these digital values. So once I start, there's 2 different strategies I can use. One, I can use a very, very simple strategy of using a counter to drive this register. So I will start off at 0 and count up from 0 to some value in binary until my reference voltage just slightly exceeds the magnitude of my unknown voltage, at which point I'm done. The bad news is if I have very, very large voltages to where I have to count up to a very high number in my range, it's going to take a long time to do the conversion. On the other hand, if my signals are very small and I'm starting the count from 0 and I work up, then my conversion times are going to be very slow or very short. And so To have a constant conversion time, what we do is we use a different approach. So again, one approach is counting, the other approach is bitwise. So first thing I do is just like the weights. I start with the heaviest weight and I compare it to the unknown. If it is lighter, if the heaviest weight is heavier than my unknown, then I remove the weight and I add the next weight. If it's larger, if the inverse is true, then I continue adding weights until I come up with the best value. And so the ideal, or the characteristic that is very attractive in the successive approximation using a bitwise approach is that the conversion time is constant. Okay, so just for every single, with a successive approximation time, I have an analog sampling time, and I have a finite amount of time during which I'm going to acquire the signal in the sample and hold amplifier, at which time then I start the conversion. And the conversion is going to take a finite amount of time as well. And so this is what we have to deal with when we're actually using the analog to digital converter. We have to allow for how much time it takes to actually charge up the sample and hold amplifier, and then we have the time it takes to actually do the conversion. So coming back to our process here, the other thing that's a key component in this is we are taking our digital value, whether we do it bitwise or counting, we feed that to a digital to analog computer or digital to analog converter. And so what we do here is we use, again, our friendly op amp. In this case, we're using a specific model. This is another example of this. And what we're doing is we're using a summing amplifier to now, using different ratios of resistors, give different weights to our input signals so that we can come up with a reference voltage that is going to be compared to our unknown reference voltage. And the nice thing is I can go through and do these individually so that I can now come up with an estimate, and my control unit is what's going to control the opening and closing of those switches. Okay, so the process is summarized here. So we start the operation. We basically will now sequence through binary values. That binary value is basically used to generate the analog voltage that we compare to our unknown input signal. And when I've gone through all the bits, then I generate this end of conversion signal. So I know the conversion is complete. And again, the sample and hold amplifier, conceptually, the way we look at it is it's like charging up a resistor. We have a resistor in here, or we have resistance in the circuit, and we charge up a capacitor. And this capacitor is going to hold a constant value to which we're going to compare our unknown. Well, this is our unknown voltage, and this is our sample of the unknown. And so this will hold a sample of the unknown voltage constant while we're doing the conversion process. Okay, so again, timing, we have to consider both steps, the acquisition and the conversion. So now let's look at our analog to digital converter. And we're going to see that we have 16 analog lines, and these analog lines can feed into, we have a couple multiplexers, and so we need to identify which multiplexers we're going to use. We have the opportunity to be able to scan through channels, and we can also, we can configure all of these inputs in a myriad of ways. We also, once we've done the conversion, we're going to put those results into the ADC buffer, and we will also have options in how we can format that data. So if I look at a slightly different version of this analog to digital converter, then what we see is we have our reference voltage. So I can use my internal reference voltages, 3.3 volts and 0, or I can feed in my own reference voltages, which may be necessary if I'm using systems that are other than MOS type technology digital logic values. Could be large values, could be smaller values. I have to look at the voltage ranges that I'm capable of supporting with this analog to digital converter circuitry. Okay, so then I have my multiplexers, which I need to select, and I will compare those to my voltage. And so I'm going to have the scan control, and then I basically have my configuration. So there's lots of logic involved with, or a lot of options involved with configuring this analog to digital converter. So if I start looking at the SFRs, and of course this is kind of a, we see that we have a number of options. And so what I want to do is I want to go through a sequence of operations that we need to do to actually make this analog to digital converter work properly. Okay, so what we're going to do is we're going to switch gears here a little bit, and let me go to this one here. Okay. So we see that this is the reference manual for the analog to digital converter. And we see that we have up to 16 analog pins. We have external reference pins, as I mentioned. We have one sample and hold amplifier. So we're going to process one sample at a time. We can scan through these channels automatically if we wish. We can control when we take the samples, when we trigger the conversion process. We can do that all manually, or we can do it automatically as well. We have a result buffer, and we can select our format for those, and we can dictate how we actually fill the buffer. And we see the format options, and then we can also continue operation during sleep and idle modes. Okay, so let's go through what does it take to actually configure these analog to digital converters. And then we'll talk about how we use them on the MX7. So let me get my notes organized here for a second. Okay, so to configure the analog to digital converter, it's a multi-step process. Now, what I've done is I've put it here. So you may have noticed that we have 3 configuration registers, and I don't want to bounce back and forth because I get comments that bouncing back and forth is a little because of the video that you see. So what I see and what you see is a little bit different in terms of delay and so on. So first thing we have to do is we have to configure analog port pins. And recall, our analog pins are basically a subset of the digital port pins that we have. And so if I'm going to use a pin as an analog pin, I have to ensure that it is not also configured as a digital output, because if it is, the digital output signal will feed right back into the analog input, and basically the analog input pin will be tied to that output voltage, whether I wanted it to or not. So I need to watch out for sharing, and we need to, when we start looking at real life usage, we'll look at the MX7 reference manual to see what is also shared with the pin we wish to use. So first thing, we have to configure the analog port pin. Next thing we have to do is we have to select which analog inputs are going to be fed to the multiplexers. So you saw we had 2 multiplexers, so we need to decide where are we going to feed those inputs. We also have to select which format do we wish to use for our result. And there's several formats there that we can select from. We need to select a clock source. So I can use peripheral bus clock, or I can use an external clock. And so I need to determine which clock I wish to use. I also need to select which reference voltages I wish to use. Do I want to use my internal voltages, or do I want to provide an external voltage? If I wish to scan, I need to specify the scan mode. So this is when I have multiple inputs, then I need to decide how I'm going to process those inputs. Now, in many instances, I'll also want to use interrupts. So I might want to generate an interrupt for a single conversion or multiple conversions, and so I have that flexibility as well. Now, we have 16 slots in our buffer. We need to specify how we want to fill that buffer as well. We have multiple multiplexers. We need to select which one we wish to be connected to the analog to digital converter. And then I have a clock source, so I have my sample clock and I have my conversion clock. So I have two different options that I can configure there. And sample time. So what I want to do, what I'd like to do is I'd like to be able to either manually control the acquisition and then the conversion time, or maybe I want to do that automatically. And so if I want to do that, I need to specify how long do I allocate for the sample time before I automatically now trigger the conversion time. If I wish to slow down the clock, I have a prescaler which I can also use. And then finally, after I've selected all of the options, I need to actually enable the analog to digital converter. Just like every other peripheral that we've talked about, we have to also enable it as well. Okay, so after you breathe a little sigh of relief saying, whew, we've gone through the whole list, now let's actually think about what do we need to do to be able to use this on the MX7. So we see that, okay, we're going to select an analog line, and what we need to do now is we need to figure out, does that line share a signal with other pins or not? So first thing we want to do is we want to go to the MX7 reference manual. And an easy way to do that is to look at the PMOD connectors. And so with a little bit of research, I decided that I want to use analog line number 4. And so this is AN4. And it happens to be on a PMOD connector A, pin 3. And so I look at this and I say, well, let's see, AN4, this is also shared with this C1 in 1 plus the change notification 6 plus port B pin number 4. So if I'm planning to use any of the port B pins, I'm going to have to be very careful that I don't intermingle, or have to be careful that I don't mistakenly use both a digital output or input and convert, and also at the same time use it as an analog input. And so when we go through the configuration, we'll see how we're actually going to do that. So I mentioned one of the steps is we had to select our analog lines. And if I come back to the list here, oops, sorry, wrong one. You'll see that I'm going to use this AD1 PCFG. And this is where we select our analog line. And the thing is this is one of the SFRs associated with the analog to digital converter. So you see this AD1 PCFG, so that's at a BF80 9060. I have a small screen here, so I gotta have my binoculars on, which I'm sure is probably an issue for you as well. But these are also in the slides, and they're also in the reference manuals. So this table of SFRs is there as well. Okay, so what I have to do is I have to go through that process. So let's look at some actual code and see how that actually is going to work. Okay, so this is an example which, and I'll show you a live demo here in a little bit. I have to do a little camera jockeying around to show you. But what I'm going to do is I'm going to now use the analog digital converter as well as the LCD display. What I'm going to do is implement basically a digital voltmeter. And so first thing I have to do is I have to determine which input I want to use. And because of the naming nomenclature on both the MX7 and the analog to digital converter, this port 4 or pot 4 is basically specifying AN5 because it's starting AN1 through N, and recall we start our bit counting at 0. So this is the 5th one in the sequence. Now when I select my analog inputs, what I'm doing is I'm using the 5th bit And recall how we number 0 to 3, 4 to 7. So when I'm looking at those bit numbers, this is going to require me to set that individual bit to a 0. When I set that bit to 0, it says that bit is going to be an analog input. All the others are set at the value 1, which says they are not analog inputs. And so this is a critical thing I need to do with my analog inputs. And if you read in the reference manual, they describe the setting of these analog input values, the bit values, and so basically a 0 corresponds to analog input, 1 corresponds to digital. And so we see we have only one bit set 0. And then I'm also going to, because I'm doing a digital voltmeter, I need to identify, I have to calculate the weight per bit, and so this is how I do that. I have 3.3 divided by 1023, and that's the weight of my least significant bit in my function. So I have a function, two functions. One is to initialize the analog to digital converter, and the second is to read the value. So the specific manual for the ADC settings is the following. So this is the, oops, gave you the wrong one, sorry. No, this is the right one. Okay, so each of the peripherals has its own chapter of the reference manual. Those are all posted on Learn. And so if you want the detailed information, and in fact, a lot of the additional information is in these reference manuals. So this explains basically the sequence you have to do. It gives you examples of how you use it and so on. And so this is a detailed reference manual. And if you go to the data sheet, so this is the section of the data sheet for the analog to digital converter. It gives you a succinct description, the block diagram, the SFRs with a minimal discussion of the key SFRs, and that's it. So we see next thing is the CAN controller. So the data sheet is basically giving you the minimal information you need to be able to hopefully be able to use peripherals. But if you want the detailed information to really understand how you have to configure it, then go to the reference manual chapter associated with that component. Okay, so we say, all right, we're going to use AN4. We said, okay, I verified I'm not using the ports as I need to do. I'm using these values to be able to calculate my voltage in. And so what I'm going to do now is I look at my functions. We have three configuration words. Sorry, bump my mouse in. So we have three configuration words. So first off is this mask specifies which bits are going to be the analog inputs. Then we have our three configuration. We have our scan. So this is my scanning SFR. We have three configuration SFRs. And this last one here, so I didn't use all the mnemonics that were associated with it, but rather I used the actual values to write to the configuration words. And this one here is basically the timing one that says how many clock cycles do I need so that I basically meet the minimum time requirements for my sampling. So this is telling me how many clock cycles am I going to use to do my acquisition time, at which time I will automatically switch to conversion. And then I turn on the analog to digital converter. So basically what I'm doing here is a shorthand implementation of those 13 steps that I just showed you previously. Then to read the analog to digital converter, what I'm doing is I'm basically selecting my channel. So this is the analog input I wish to sample. I start the sampling. I set the sample flag to 1. This starts the sample and hold amplifier because I configured it up here for automatic handoff. After 4 clock cycles, then I'm going to now switch to conversion mode. And what I'm doing now is I'm waiting for my done to indicate that the conversion is complete. at which time the data from the D to A, that is the estimate, is written over to the buffer. So I basically read that buffer, and now I have my value. So in my code, what I'm doing is when I read the value, I'm going through a loop, he says. Okay, so I just read my A to D, and again, these are peripheral library functions that we can use, but the configuration was done using the SFRs directly. And so what I'm doing here is now I'm just reading, and this pod is my AN5 or port number 4, and then so that brings me an integer value. I'm going to convert it to a fractional value, and so this is just counts. How many counts? What is my binary value? I want to convert that to voltage, and then I want to be able to display it. So I take that value, and what I do is I convert it to a string. I'm showing you the wrong one. This one doesn't do well, this is just displaying the counts here directly. Okay, so let me open a second one, because this is one that you, let's see. Okay, so now what I'm doing is this was my previous example where I'm just printing out the counts. And what I need to do is I need to actually now determine the bit value. So what I did previously is I calculated the bit value, which was basically my input voltage, my reference voltage max minus my reference voltage min, and divided by the count. And so by doing it this way, rather than hard coding in 3.3 volts, what I've done is I've basically now allowed this code to be used in situations of where I'm not going to use just those stock voltages. I have the flexibility of putting in different values without having to redo all the code. I have it in one location. So I determine the value of the bit. I read the values from the A to D, and now I calculate a analog value. So first thing I do is I convert my counts value to a float, so that these are all now float values, and I do that calculation. I print that value to a string, and now I display it on my LCD display. So pretty straightforward in terms of the process. So let me give you a short demo of that. So pause for a moment. Let me do some video recalculate or reconfiguration here. Move things around a little bit. So get this camera reconfigured here properly. Let me zoom it out a little bit. Okay, so let me fire up this guy. And let's see if... So now you can see a voltage value on there. So what I'm doing is in this upper part of the screen, you can see that I have my little breadboard there. It has a voltage divider circuit, and if you've looked at any of the lab videos, then you've seen some of this. but I have a voltage divider circuit there, and I'm changing the voltage across this potentiometer. And so what I'm going to do is I'm going to change the voltage, and you can see on the LCD display, and let's see, maybe this will, I don't know if that helps the contrast any, or I can get a little closer. And so what I'm doing again is I'm changing my voltage, and you see I'm lowering the voltage across my resistor, feeding that into the analog to digital converter, and you can see that the voltage is changing accordingly. And so this could be a sensor, this could be any number of things, and so I would use that voltage that I've read to do some sort of function that would allow me to be able to take advantage of having an analog input. Okay, so any questions on the analog to digital converter? Okay, so what I want to do next is I want to talk a little bit about another capability that we use in our microcontroller. So let me switch off this camera if there's no other questions, and so let me pause here for a moment. I'm going to stop the video, get this out of the way here. Get my nest of wires so I don't fall. Okay, so we're back. So let's talk about another capability that exists on the PIC32. And this is one where we start talking about actually controlling actuators. And this function is what is known as output compare. So everything that we've talked about so far has been related to digital signals until just recently, where we talked about using analog inputs. Well, we also want to control actuators and other devices that allow us to be able to maybe change voltages selectively, or maybe position motors and so on. And so we're going to find that we have a number of capabilities that we can use to allow us to be able to drive actuators, and even we can also generate sine waves and things like that. And so what we're going to do is we're going to take advantage of the fact that we can generate square waves. And the way we're going to do that is using what is called the output compare. And the way that function works is we're going to generate pulse width modulated signals. And the fundamental concept that we need to think about when we generate square waves is we can actually change what is called the duty cycle. And the duty cycle relates to the percent of time that the signal is high to the overall period. So the period is the time from one cycle to start to the next cycle, as you're all familiar. So with a nominal square wave, I have a duty cycle of 50%. So 50% of the time the signal is high, 50% of the time the signal is low. So my average DC voltage in this case is going to be V over 5. So if I integrate it from time 0 to T, I'm going to, and the magnitude here is V, my average voltage is going to be V over 2, okay, or 1/2. And if I, or 0.5 of V, so that's V over 2. Now if I change the duty cycle such that the percent of time that this signal is high to the overall time, then my average DC voltage is going to get lower and lower. And so I'm not set up to do the demos today, but I'll give you the demos on Thursday showing how we can generate DC levels that are basically going to vary by changing the duty cycle. And so I can control things like lighting, motors, and other sorts of things by varying this percent of time that my signal is high to the time the signal is low. And we have a very, very handy capability that we can use to be able to implement that. And the way we do that is we're going to, so what we're doing here is we're just talking about PWM signal applications. And so I'm going to change my average DC value. So where do I use them? I can use them for things like speed control, lighting. I can also, depending on the nature of how I've configured this, position armatures of servo motors, and we'll talk about servo motors in a little bit later. I don't want to talk about that yet. But what we're going to do is we're going to use our timers. And before we jump into that, if I have a square wave, I also mentioned that we can also generate sine waves. And so let me get this out of the way here. So there is a copy of an example ADC code on Learn. So there was a question there about that code, and if it's, I'll double check if it's not available to you. I'll make sure that it's available to you immediately after the lecture. And so if I look at a square wave and I look at it mathematically, and I do the Taylor series the Taylor series expansion, I see that this is actually equal to a sum of the odd harmonics of a fundamental frequency. And so when I generate the square wave, if I wanted a sine wave, if I could, and notice the magnitudes of these square waves decreases. And so if I wanted to generate a sine wave, I have, depending on the frequency of the sine wave, my device may or may not be responsive to the harmonics, or I could just filter off the upper harmonics using a capacitor or simple low-pass filter to be able to do that. So we can actually generate sine waves using our output as well. And the way we're going to do that is we're going to use our timers. So recall our timers will count from 0 to whatever value is in the preset or the period register, at which time it's going to now go back to 0 and count up to the value in the preset. And so this will happen continuously, even if the interrupt flag is set or not set. The timers are designed to basically reset once the timer register value is equal to the preset register value. And that's what the comparator is going to do for us. So we have an output compare function that we can configure to basically generate pulse width modulated signals. And so what we do is in this output compare, what we do is we have a compare register and we set it to some value. So as long as the timer value is less than the value in the output compare register, then the output is going to be, on this configuration that we have, is going to be high. And so by lowering the value, we can lower the duty cycle of the signal. If we raise it, the output will remain high longer, and so we will basically be increasing the duty cycle. And so this is a function that we're going to use to allow us to be able to generate pulse width modulated signals. And so I will set up another demo to show you how we use these and how they can actually be used to control peripherals, and how we can also use them to control servo motors. So the way it works is we have the following. We have our timer that is going to basically be generating our reference signal. So we have to specify which timer. And what it's going to do is now we have this output compare register that is going to basically look at our timer input, and it can be a 16-bit or a 32-bit timer. So we can set that up as appropriate. And it will generate the output compare. So we have our output compare logic, which will allow us to use a few different modes that we can basically configure our output. And so one of the things that happens in this PIC32 microcontroller is if it is in the middle of an operation and we're trying to change this output compare register, the system does not operate, or does not, I'm going to say, it doesn't like you changing those values when they're being used. So the way the designers have dealt with that is they basically have a secondary register to which we write our changed value. At the appropriate time, when it's not affecting operations, what is in this backup register is copied to the operational register, and that is now used for the next compare operation. So when it is appropriate, this backup value, which we're continually updating if we're changing the duty cycle, is transferred to the compare register, and this is now used for the operational use to generate the output compare output. Okay, so what we're going to do is we're going to use this to control devices to vary DC voltages, and we're also going to use it. So I'll give you some examples. I'll also show you generating sine waves, and I have to be a little creative in how I instrument it so you can see it, but we'll do that so that you can be able to actually view this operation taking place. And so the SFRs are pretty straightforward. We just have to turn it on. We indicate whether we operate in the idle mode. We indicate whether or not it's going to be at 32, and there are specific timer requirements that we need to follow when we use output compare. And so there are predetermined timers that I need to ensure I give you the right value, and I could get the reference sheet, but so, and then we specify how we generate the output with the remainder of the SFRs. And then we have our compare register, the primary and the backup, and so that's basically what we need to generate output compare. So we'll use output compare to generate outputs. We'll use our analog input to generate values that we can use to, and in fact, in one of my demos, I have the A to D feeding values that we use to vary the output compare. And if we had time this semester, we had a 2-week delay because we weren't allowed to have any assignments for the 2 weeks after spring break, then we would have had an additional lab where we would be driving servo motors using either the output compare or timers to do something similar, and we'll talk about using timers as well. So to recap, what we've talked about is we have talked about using the analog to digital converter. We know that we have in our PIC32 we have a successive approximation analog to digital converter. There's two classifications of ADCs. One is direct conversion or flash. The other is successive approximation. They two operate differently, and the time required to be able to do that varies between the two. Of course, the flash is like immediate, and the successive approximation takes a little bit of time. In fact, our system takes 12 clock cycles for the conversion time and 4 clock cycles for samples. So we see that's 16 clock cycles to be able to do a single sample. When we use those, we have higher precision with successive approximation just because of the real estate and the power required to do it. Configuring our particular ADC is a little bit more involved because of the complexity. We have a lot of different steps, but depending on our applications, if you have many A to D or many analog signals, that is easily within the capability of the system. If you have just a single one, then it's a lot simpler, and the kinds of applications we're doing, we might have 1 or 2 kinds of inputs, and so it's not going to be anything too tremendously difficult once we get a little experience configuring them. So A to Ds, fundamental for any kind of digital application where you're working in the real world, because we have sensors that are going to give us analog signals. So you have to be able to bring those signals in and process them accordingly. There are a few little things you have to be aware of, which we talked about last time. So we want to make sure that we sample on a regular basis. Sometimes it helps to have an interrupt source, a clock, to allow us to do this on a regular basis. We need to make sure that we are sampling at we have enough resolution to be able to do the things we want to do. And in this case, we have 10 bits of resolution. We want to make sure that we are not inputting signals of such high frequency that the results are going to be distorted due to aliasing. And so those are some of the other considerations you need to take into account. And one of the ways we do deal with aliasing is oftentimes you'll see a low-pass filter on the signal that's coming in to basically filter out any high-frequency content so you don't distort your signal. So ADCs are an important part of real-world applications, and I encourage you to view the Lab 8 videos, become familiar with those operations, and you'll see that and the sample code that I also post, I would play with it. Well, you can't play with it because you don't have the hardware, unfortunately, but I wish you did, because this is some of the things that I think are very, very valuable to you. So if you do have the hardware, by all means, play with the analog to digital converter. Okay, well, that's enough rambling for today. Any other questions? And we'll have a few more demos, and we'll actually see some motors operating next time as well. I'm going to set it up for more of a hardware-oriented kind of demo, so I just have to do my cameras a little bit different. Any other questions? Oh, one last thing. The online course reviews are also available. I ask that you take a couple minutes and give me a little bit of feedback, and I would appreciate if you would do that. So if there's no other questions, I'm going to stop the recording now, and I will see everybody on Thursday.